Welcome to this coding problem walkthrough. Today, we'll be tackling LeetCode problem number 2038, remove colored pieces if both neighbors are the same color. This is a fascinating problem that involves simulating moves in a game while applying logical constraints. Let's dive in and explore the approaches to solve this step by step. In this problem, Alice and Bob are playing a game with a string called colors, which consists of only the characters A and B. The rules of the game are straightforward. Starting with Alice, they take turns removing a single character from the string. However, a character can only be removed if it has both neighbors of the same color as itself. For instance, in the string AAA, Alice could remove the middle A, but not the first or last A, since those don't meet the condition. Once a character is removed, the string shortens, and the arrangement of neighbors changes, potentially creating new opportunities for removal. If a player cannot make a move during their turn, they lose that turn, and the game continues until no more moves can be made. The winner is determined by the number of moves each player makes. Alice wins if she has made more moves than Bob, and Bob wins in all other cases. The task is to determine the winner of the game based on the input string colors. Specifically, you need to return true if Alice wins and false if Bob wins. Let's look at some examples to understand this better. In the first example, the input string is colors equals ABAB. Here, Alice can remove one A from the group AAA, leaving the string as ABAB. When it's Bob's turn, there are no valid moves for him since no character satisfies the condition of having both neighbors the same color. As a result, Alice wins because she made one move, while Bob was unable to make any moves. In the second example, the input string is colors equals AA. In this case, no character in the string has both neighbors of the same color. Since neither Alice nor Bob can make a move, no moves are made throughout the game. By default, Bob wins in this scenario, so the output is false. In the third example, we have the input string colors equals ABBBBBBBAA. Here, Alice goes first but cannot make any moves because no character satisfies the removal condition, as there are no groups of 3 consecutive characters. Since Alice is unable to make a move, the game ends without any moves being made, and Bob is declared the winner. Bob wins in the last example because no moves could be made, and Alice did not make any moves during the game. Now, let's consider the constraints and edge cases. The length of the string colors can be as small as 1 and as large as 100,000, and it will always consist of characters A and B. For edge cases, if the string length is 1, no moves can be made, and Bob automatically wins. Similarly, strings with no consecutive groups of the same character, like ABABAB, will also result in no moves, leading to Bob's default win. On the other hand, strings with large consecutive groups of the same character, such as AAA, allow players to make multiple moves until the group reduces to fewer than 3 characters. These examples and constraints highlight the different scenarios you'll need to consider when solving the problem. To solve this problem, we can explore a few different approaches. The first is the brute force method. The intuition here is to simulate the game step by step, alternating turns between Alice and Bob. On each turn, you identify all removable pieces for the current player and remove them. This process continues until no more moves are possible. At the end, the winner is determined by comparing the total number of moves made by each player. While this approach is simple to understand, its implementation involves repeatedly traversing the string to remove characters, leading to a time complexity of O(n)(. This makes it computationally expensive and impractical for larger strings. Next, we have the optimized count-based approach, which avoids simulating the game altogether. Instead, we focus on a key observation: the number of moves a player can make depends on the number of consecutive pieces of the same color. For example, Alice can remove A pieces if there are at least 3 consecutive A's, and Bob can do the same for B pieces. For every group of consecutive A's or B's of length K, the respective player can make K2 moves. The implementation involves parsing the string to count these potential moves for both players and comparing their totals to determine the winner. This approach is far more efficient with a time complexity of O(n), as we only traverse the string once. Its simplicity and efficiency make it a strong candidate for solving this problem. Now, another method to consider is the sliding window technique. Here, we use a sliding window of size 3 to scan through the string and identify removable pieces. As the window slides, we count moves for Alice when we encounter 3 consecutive A's, and for Bob when we see 3 consecutive B's. This method also runs in O(n) time since it involves a single traversal of the string. However, it requires manual management of the sliding window, which can make the implementation slightly more cumbersome compared to the count-based approach. Ultimately, the optimized count-based approach stands out as the most practical strategy. It directly leverages the observation that the game depends only on the lengths of consecutive groups of the same color. By focusing on these groups, we avoid the overhead of simulating the game or managing a sliding window. While both the count-based and sliding window methods are efficient with O(n) complexity, the count-based approach is simpler to implement and less error-prone. Additionally, it is exponentially more efficient compared to the brute force method. This balance of efficiency and simplicity makes the count-based approach the ideal solution for this problem, as it aligns perfectly with the problem structure and avoids unnecessary complexity. The problem we're addressing revolves around a 2-player game where players take turns performing actions, such as removing pieces, until no moves are left. The winner is determined by comparing the number of moves made by each player. To tackle this, we start by initializing the game state. Depending on the nature of the game, the state could be represented as an array for a sequence of elements, a 2D matrix for a board, or another structure that fits the problem. Alongside this, we'll set up counters for tracking the moves made by each player, such as Alice_moves and Bob_moves. A flag, like current_player, will indicate whose turn it currently is. Next, we define the rules for valid moves. A function will iterate through the game state, checking whether the current player can perform specific actions. For example, if it's a piece removal game, the rules might specify which pieces the player is allowed to remove. Establishing these rules clearly ensures that each action is legal and aligns with the game's mechanics. With the game state initialized and the move rules defined, the next step is simulating the turns. This involves alternating between Alice and Bob in a loop until neither of them can make a valid move. For each turn, we first check if the current player has any legal moves available. If they do, one of these moves is executed, updating the game state accordingly. Then, the move counter for that player, such as Alice_moves or Bob_moves, is increment. Logging the move can be helpful here, either for debugging or visualizing the sequence of actions. If no valid moves are available for the current player, we log this outcome and switch to the other player. Once the loop ends, determining the winner is straightforward. By comparing the move counts of Alice and Bob, we can declare a winner, whether it's Alice, Bob, or a draw in case of equal moves. Additionally, edge cases must be handled carefully. For instance, if the game begins with no valid moves for either player, it should be declared a draw immediately. Efficiency is also critical, especially for large inputs. Unnecessary computation should be avoided, and scenarios where one player dominates early should be handled seamlessly. This simulation-based approach ensures correctness by mimicking the game's rules step by step. However, simulating every move can become computationally expensive for larger game states, so optimizations may be necessary. Alternating turns between players is critical to ensure fairness and maintain the game's flow. The rules for validating moves are at the core of the simulation, as they prevent any illegal actions and ensure the game progresses logically. The termination condition is simple: the game ends when neither player has valid moves, which keeps the loop structure clean and easy to implement. To support these operations, the choice of data structures is essential. For example, a 2D matrix works well for board games, while a list might suffice for sequence-based games. The valid moves for a player can be stored in a list or set for efficient iteration and checking. Simple counters track the number of moves made, providing the data needed to determine the winner. Breaking the operations down further, finding valid moves involves iterating through the game state and evaluating each position based on the rules. This could range from simple checks to more complex logic, such as verifying adjacency or other constraints. When executing a move, the game state must be updated carefully, modifying the underlying data structure to reflect the action while ensuring consistency. Switching turns is handled by toggling a flag, like current_player, to alternate between Alice and Bob. To improve efficiency, several optimizations can be applied. For example, if a player has no valid moves, we can skip their turn immediately, avoiding unnecessary iterations. Pruning techniques help by focusing only on parts of the game state that have changed, rather than recalculating everything from scratch. Pre-computing patterns or configurations, where applicable, can reduce the cost of validating moves. In terms of complexity, the time required depends on the number of positions in the game and the number of turns taken. For n positions and m turns, the time complexity is approximately O(n*m). The space complexity, on the other hand, depends on the data structures used, such as O(n) for an array or O(n)² for a matrix. To solidify our understanding, let's walk through an example. Imagine a simplified game where players take turns removing stones from a pile. The game starts with 5 stones. Alice goes first and removes 1 stone, leaving 4. Then Bob removes 2 stones, reducing the pile to 2. Alice takes another turn, removing 1 stone and leaving just 1 stone in the pile. Finally, Bob removes the last stone. At the end of the game, both Alice and Bob have made 2 moves each, resulting in a draw. This step-by-step process illustrates how the algorithm handles alternating turns, updating the game state, and counting moves. Even for more complex games, this structured approach ensures clarity and correctness, making it easier to trace the logic and verify the results. Here, we define a class called solution and implement the method winnerOfGame. This method takes in a string, colors, which represents the sequence of colored pieces on the board. We start by initializing 2 counters, Alice_moves and Bob_moves. These will keep track of the number of valid moves Alice and Bob can make, respectively. Next, we use a while loop to traverse the string and analyze consecutive segments of the same color. The outer loop begins at index I, and within it, we use another pointer, j, to count how many consecutive pieces have the same color. This continues until we encounter a different character or reach the end of the string. Once we determine the length of the current segment, we check if it is greater than or equal to 3, since a move can only be made if there are at least 3 consecutive pieces of the same color. If the segment qualifies, we calculate the possible moves for Alice or Bob based on the color of the segment. For example, if the segment is made of A, we increment Alice's moves by the segment length -2, as the first and last pieces in a group cannot be removed. Similarly, for segments of B, we update Bob's moves. Finally, we increment I to continue analyzing the next segment. The method concludes by returning a Boolean value that determines the winner. Specifically, Alice wins if the total number of moves she can make is greater than the total number of moves Bob can make. This is achieved by simply checking if Alice_moves is greater than Bob_moves. If the condition is true, the method returns true, indicating Alice is the winner, otherwise, it returns false, meaning Bob either wins or it's a tie. This approach ensures that we only traverse the string once, making it efficient while correctly evaluating the number of moves each player can make based on the game's rules. Here, we begin our Java implementation of the problem by defining the class solution and the method winnerOfGame, which takes a string colors as input. This string represents a sequence of colored pieces, where A stands for Alice's pieces and B stands for Bob's pieces. We start by initializing 2 counters, Alice moves and Bob moves, to 0. These will track the number of valid moves each player can make. Next, we use a while loop to iterate through the string. Inside the loop, we initialize a pointer j at the current position I and use another while loop to count the length of consecutive characters that are the same. This helps us identify segments of pieces belonging to the same player. Once we determine the length of the segment, we check if it is greater than or equal to 3, as only segments of this length or longer allow for valid moves. If the segment meets this condition, we calculate the possible moves for the player based on the segment's length. For Alice, represented by A, we add segment length 2 to Alice moves. Similarly, for Bob, represented by B, we add the same value to Bob moves. After processing a segment, we update I to point to the next segment by setting it to j. After iterating through all the segments in the string, we calculate the result. The method returns true if Alice has more possible moves than Bob, indicating that she is the winner. Otherwise, it returns false, meaning Bob wins or neither has enough moves to win. This logic ensures that the solution directly compares the number of moves each player can make, which aligns with the problem's requirements. By carefully counting segments of pieces and computing possible moves, the implementation efficiently determines the winner based on the given string of colors. To solve this problem, we start with the input string colors equals ABAB. First, we initialize two counters, Alice_moves and Bob_moves, both set to 0. These will track the valid moves Alice and Bob can make. We then iterate through the string, starting at index I equals 0. The first step is to identify the segment of consecutive A's. As we iterate, j increments from 0 to 3, and we calculate the segment length as j I equals 3. Since this segment length is at least 3, Alice can make one move, calculated as segment_length 2. We update Alice_moves to 1 and move the pointer I to 3 to continue processing the next segment. At index I equals 3, we encounter a single B. Since the segment length is less than 3, no moves can be made, and we increment I to 4. Next, at I equals 4, we find another segment of consecutive A's, but this time, the segment length is only 1. Again, no moves are possible, so we update I to 5. Finally, at I equals 5, we identify a segment of consecutive B's with a length of 2, which is also too short for any moves. We increment I to 7, and at this point, we've processed the entire string. With the end of the string reached, we finalize the counts, Alice_moves equals 1 and Bob_moves equals 0. Since Alice's moves are greater than Bob's moves, Alice wins, and the function returns true. Now, let's consider another example with the input colors equals AA. Again, we initialize Alice_moves and Bob_moves to 0 and begin iterating at index I equals 0. We find a segment of consecutive A's as j increments from 0 to 2, resulting in a segment length of j I equals 2. Since this segment length is less than 3, no moves can be made, and we update I to 2. Since we've now reached the end of the string, the final counts are Alice_moves equals 0 and Bob_moves equals 0. In this case, since Alice does not have more moves than Bob, the function returns false. Next, for the input colors equals ABBBBBBBAA, we again initialize Alice_moves and Bob_moves to 0 and start iterating at I equals 0. At this index, we find a single A, which has a segment length of less than 3, so no moves can be made, and we increment I to 1. At I equals 1, we find a segment of consecutive B's. As j progresses from 1 to 8, the segment length becomes j I equals 7. Since this length is at least 3, Bob can make segment_length 2 equals 5 moves. We update Bob_moves to 5 and move I to 8. At I equals 8, we find a segment of consecutive A's, but the segment length is only 2. No moves are possible, so we update I to 10. With the end of the string reached, the final counts are Alice_moves equals 0 and Bob_moves equals 5. Since Alice does not have more moves than Bob, the function returns false. The time complexity of this solution is O(n), where n is the length of the input string colors. Let's break this down step by step. First, the outer while loop iterates through the string using the variable I. On each iteration, I skips over a segment of consecutive characters, such as AAA or BBB. Since each character in the string is processed exactly once, this contributes O(n) to the complexity. Next, there's the inner while loop, which increments j to determine the end of each segment of consecutive characters. Even though this is a nested loop, the total number of iterations across all segments still adds up to the total number of characters in the string, meaning it also contributes O(n). Finally, for each segment, we calculate its length and determine the number of valid moves. These are simple arithmetic and conditional checks, which are O(1) operations. When we combine these steps, the overall time complexity becomes O(n) plus O(n) plus O(1), which simplifies to O(n). The space complexity of this solution is O(1), as it requires only a constant amount of additional memory. The algorithm uses a few scalar variables, such as Alice_moves, Bob_moves, I, j, and segment_length. Each of these requires constant space, so their combined contribution is O(1). Importantly, the algorithm does not use any extra data structures like arrays or hash maps. Instead, it processes the input string directly without modifying it. This ensures that no additional memory is allocated beyond these fixed variables. Now, if we consider the best, average, and worst cases, the time complexity remains O(n) in all scenarios. In the best case, where there are no segments of length 3 or more, such as in the string ababab, the algorithm still processes all characters once. In the average case, where there is a mix of short and long segments, each character is still processed exactly once. Even in the worst case, where the string is a single long segment such as quad A, the algorithm processes each character only once. This consistency reinforces the O(n) time complexity. Let's compare this solution with a brute force approach. A brute force method might involve simulating the game by repeatedly removing valid pieces and scanning the string for moves. This would involve multiple passes over the string, leading to an O(n) superscript 2 time complexity in the worst case, such as when the string is very large and all moves are valid. In contrast, the current solution achieves O(n) time complexity by directly counting valid moves for each segment of consecutive characters without modifying the string. To prove the time complexity mathematically, note that the outer loop runs once for every character, contributing O(n). Similarly, the inner loop advances j across all characters in the string, also contributing O(n). All additional operations, such as arithmetic and conditional checks, are O(1). Combining these, the total time complexity is O(n) plus O(n), which simplifies to O(n). As for space complexity, the algorithm uses only a fixed number of scalar variables, requiring O(1) space. This lack of additional memory usage solidifies the space complexity as O(1). One common mistake when solving problems like this is misunderstanding the problem constraints. This often happens when candidates overlook details such as the input size or specific rules, like players being required to alternate moves. These details are critical because missing them can lead to incorrect assumptions about how edge cases or scalability should be handled. To address this, it's important to carefully clarify all constraints before starting your solution and then explicitly test your implementation on edge cases, such as an empty input or the smallest and largest possible values. Another frequent pitfall is relying on inefficient brute force implementations. While brute force can be tempting, repeatedly looping over all elements without considering optimizations can cause your solution to time out on larger inputs. Techniques like memoization or pruning redundant calculations are often necessary to improve efficiency. Lastly, ignoring how the game state is represented can lead to higher complexity and harder debugging. For example, using a list when a set or queue would be more efficient can drastically affect performance. To avoid this, choose data structures that are well suited to the kind of operations you need, such as constant time lookups or logarithmic time inserts. Another critical oversight is failing to account for player strategy in competitive games. Often, candidates assume only one player's moves matter, but in reality, both players will play optimally. Ignoring this can lead to incorrect results because you're not simulating the actual dynamics of the game. To fix this, make sure to explicitly simulate both players' moves, always assuming they are making the best possible decision. Skipping edge case testing is another common issue. For instance, not considering scenarios where no moves are possible, or the game ends immediately, can leave your solution incomplete. Testing on edge cases, such as minimal inputs, ties, or situations where only one player can make a move, is essential to ensure robustness. From an interview perspective, it's also helpful to recognize common patterns across game theory problems. Techniques like the minimax algorithm, dynamic programming for state tracking, or greedy approaches for move selection often reappear. Being able to identify these patterns quickly can save you valuable time. Additionally, clear communication is key. Explain how you handle game states, turns, and termination conditions. Interviewers want to understand your thought process, not just the correctness of your solution. Be prepared to discuss trade-offs as well, such as when brute force might be acceptable versus when optimizing with techniques like dynamic programming or alpha-beta pruning is necessary. There are several related problems that can help you practice and deepen your understanding of similar concepts. For example, LeetCode 877, known as Stone Game, is a classic game theory problem that uses dynamic programming to determine the winner. Another related problem is LeetCode 486, Predict the Winner, which also focuses on predicting the outcome when both players play optimally. LeetCode 1140, Stone Game 2, builds on the original Stone Game by adding additional constraints, while LeetCode 1563, Stone Game V, introduces more advanced techniques like prefix sums combined with dynamic programming. These problems share similar themes and can help you see how different constraints affect the strategy. As for alternative approaches, the minimax algorithm is a useful strategy for small input sizes. It systematically simulates all possible moves and selects the best outcome for the current player. However, the trade-off is that minimax has exponential time complexity, which makes it impractical for larger inputs. Dynamic programming, on the other hand, is ideal when the game state can be represented recursively. By memoizing states, you can significantly reduce redundant calculations. While this approach is faster than minimax, it can still be memory-intensive and requires careful thought in representing states. In some cases, using a greedy approach can be effective. This involves making the locally optimal choice at each step, such as always selecting the maximum value available. While this strategy can simplify the solution and work for certain problems, the trade-off is that it may not account for all edge cases or future consequences. This can lead to suboptimal outcomes in scenarios where the game's later states depend on earlier decisions. It's important to carefully evaluate whether a greedy approach is appropriate for the specific problem you're solving, as it may not always guarantee correctness. Great job making it to the end. To summarize, we reviewed the problem, explored a brute force approach, and discussed key takeaways such as simulation and state-driven problems and identifying valid moves. Remember to practice similar problems to solidify these concepts. Thanks for watching, and don't forget to like and subscribe for more coding tutorials. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!